Okay, so in the 1930s, we had both Auguste Piccard and the Russians sending up high-altitude balloons, and they're looking out and they're not able to detect curvature. So we go forward about a decade to the 1940s, 1948. This is an official CIA, look up here, CIA.gov, okay, CIA declassified document from the Russians. I'm going to pull it up here in Adobe Acrobat. It's a little easier because I've already highlighted some stuff here, same document. All right, so the subject is Earth measurements, 1948, Moscow, Russia. Outer gravitational field and shape of the physical surface of the Earth. They're trying to figure out the shape of the Earth? Wait a minute. I thought we knew the shape of the Earth since Pythagoras and Eratosthenes, right? Well, apparently the Russians didn't get the memo. A study is made of the coordinates necessary for the solvability and uniqueness of solution of an integral equation by the aid of which the outer gravitational field and the shape of the physical surface of the Earth may be determined. So we go through this document a little bit here. It says the methods of studying the shape of the Earth. So this is what their goal is here. They're outlining some of that. The shape of the physical surface of the Earth can be determined with sufficient reliability on the basis only of data obtained from exact measurements. Well, that goes without saying, I suppose. And let's keep going down here. Let's see. We can regard the potential of the real Earth, by this equation here apparently, as known correct to an additive constant, whatever that is, at all points of the physical surface of the Earth and only on the surface, whereas it is not determinable at all other points of space without knowledge of the shape of the Earth. So they're still trying to figure out the shape of the Earth here. But since the shape of the Earth is not known, the shape of the Earth is not known, 1948, the true coordinates of these points, B, L, and H, are unknown to us. So the Russians are having trouble figuring out the shape of the Earth in 1948. Let's look at another document here. Another declassified CIA document up here, right? They're checking out the firmament in this one. Let's go back to Acrobat. 1953 now. Geophysics light scattering, USSR. Trying to figure out how does light work in the atmosphere here. So we get down to page 19 here. It says dissertations defended in the Scientific Council of the Institute of Physics of the Earth, Institute of Physics of the Atmosphere, and Institute of Applied Geophysics, USSR, 1957. March 1957. Looks like March 23, 1957, apparently. The dissertation represents the result of many years of study of the clear daytime sky. The observations were carried out in 12 locations at various altitudes above the sea, various climatic, meteorological, and synoptic conditions. The observations were carried out mainly during high transparency of the atmosphere in the visual range of the spectrum in the absence of a snow cover. In the investigations, 2 instruments designed by V.G. Fesenkov were used. One of these was a visual photometer of the daytime sky intended for measuring the brightness of the firmament. Interesting. Trying to figure out the brightness of the firmament. Again, 1957. The dissertation contains a certain formula of the brightness of the sky, taking into consideration only the brightness of the first order, and derived, get this now, on the assumption of a flat Earth, and giving some conclusions derived on the basis of this formula. So the Russians are trying to check out the firmament based on assumptions of a flat Earth in 1957? Very interesting, huh? Alright, let's see what NASA has to say. Looking at this ntrs.nasa.gov document here, dated April 17th, 1961. Go back to Acrobat, looking at this document from 1961. And it says, a trajectory simulation incorporating the above requirements is represented in Figure 8. In addition to the above requirements, this simulation assumes a vehicle with 6 degrees of freedom and aerodynamic symmetry in roll, and the missile position in space is computed relative to a flat non-rotating Earth. So they're checking out missile position in space computed relative to a flat, non-rotating Earth. Why would you do that? If the Earth is a rotating ball, 25,000 miles in circumference, why would you do your computations based on a non-rotating flat Earth? You're going to tell me that this simplifies the math? I mean, we are actually dealing with rocket scientists here, so math's not a problem for these people. All right, let's see what else we can find. That was April 1961. This is nasa.gov again, June 1971. So let's look at that one. June 1971. A method for reducing the sensitivity of optimal nonlinear systems to parameter uncertainty. Whatever that means. And we get down to about page 12 here. And it says, a numerical example problem statement. The example problem is a fixed time problem in which it is required to determine the thrust attitude program of a single stage rocket vehicle starting from rest and going to specified thermal conditions of altitude and vertical velocity, which will maximize the final horizontal velocity. The idealizing assumptions made are the following. Number 1, a point mass vehicle. Number 2, of the idealized assumptions that are being made for this example is a flat, non-rotating Earth. NASA making idealized assumptions based on a flat, non-rotating Earth? What's going on here? Let's continue. Here we have another NASA.gov document dated March 1972. March 1972, NASA Technical Memorandum, determination of angles of attack and side slip from radar data and a roll stabilized platform. Gotta love the titles, huh? Okay, abstract. Equations for angles of attack and side slip relative to both a rolling and non-rolling body access system are derived for a flight vehicle for which radar and gyroscopic attitude data are available. The method is limited, however, to application where a flat, non-rotating Earth may be assumed. All right, let's continue. That was 1972, the end of the, or right around the end of the Apollo program. So we go to NASA again, nasa.gov, December 1978. Investigation of aircraft landing in variable wind fields. Equations of motion. This comes up a lot. The two-dimensional model for aircraft motion presented in this section follows the general form developed by Frost. It accounts for both vertical and horizontal mean wind components having both time and spatial variations. The aircraft trajectory model employed in this study was derived based on the following assumptions. Number 1, the Earth is flat and not rotating. That's the number 1 assumption? So we're going to see this over and over and over again regarding the equations of motion. They're always using it on a flat, non-rotating Earth model, which doesn't make sense if you're developing aircraft and missiles and things like that to go over a rotating ball. Why would you start off with the assumption of a non-rotating flat Earth if the real-world application is over a spinning ball? 1987 NASA technical paper, 2768, User's Manual for Linear, a Fortran program to derive linear aircraft models. Get that in Acrobat here, same document. And we'll scroll down to, I believe it was page 12 again. Program overview. Within the program, the nonlinear equations of motion include 12 states representing a rigid aircraft flying in a stationary atmosphere over a flat, non-rotating Earth. More diagrams, more equations. The nonlinear equations of motion used in the linearization program are general 6 degree of freedom equations representing the flight dynamics of a rigid aircraft flying in a stationary atmosphere over a flat, non-rotating Earth. Let's continue. That was 1987. NASA.gov, May 1988. Flight testing. Flight testing a V-STOL aircraft to identify a full envelope aerodynamic model. June 27, 1988. Day after my birthday. Page 4 of their document. For aircraft problems, the state of measurement models together represent the kinematics of a rigid body for describing motion over a flat, non-rotating Earth. All right. NASA.gov, December 1991. Aircraft model for the AIAA Controls Design Challenge. On page 11, once again you have the equations of motion and atmospheric model. The nonlinear equations of motion used in this model are general 6 degree of freedom equations representing the flight dynamics of a rigid aircraft flying in a stationary atmosphere over a flat, non-rotating Earth. You guys starting to see a pattern here? NASA.gov, June 1997. Talking about the SR-71. Predicted performance of a thrust-enhanced SR-71 aircraft with an external payload. One of my favorite aircraft of all time. That's just a cool looking airplane, huh? Let's see what they have to say about a back-mounted hypersonic research vehicle sitting on top of the SR-71. That's pretty crazy. Pretty cool interior shot right here. And on page 8, digital performance simulation description. The digital performance simulation equations of motion use 4 assumptions that simplify the program while maintaining its fidelity for most maneuvers and applications. Number 1, point mass modeling. 2, non-turbulent atmosphere. 3, zero side forces. And 4, a non-rotating Earth. Now they don't specify flat here, but they're saying the Earth's not rotating as part of their 4 assumptions that simplify the program while maintaining its fidelity. So they're discrediting the rotating Earth right here, at least by that statement it would appear. Moving right along, you come to another NASA document. I wasn't able to figure out what year this was from, but it's definitely a NASA document here. I'm guessing sometime around 1997, or sometime shortly thereafter, as the footnotes indicate anyway. There are footnotes that go to 1997. They don't go any later than that. Singular arc optimal control. Our minimum time to climb problem. In our minimum time to climb problem, the aircraft is modeled as a point mass and the flight trajectory is strictly confined in a vertical plane on a non-rotating flat Earth. And we'll just fast forward to the end here. See, that's the dates there. The latest one is 1997, so that's where I came to that conclusion. 2000, Army Research Laboratory. This is arl.army.mil document here. Path loss measurements in a forested environment at VHF. Let's check that one out. Under data analysis on page 10 of their document here, multipath data. In this section we discuss the data for the measurements described in section 2.2 figure 9 plots the transmission loss as a function of transmit antenna height for 145, 223, 300, 435, and 910 megahertz respectively. The receive antenna height was 2.7 meters and the range was 410 meters for all frequencies except 435 megahertz, where the receive height was 3.6 meters and the range was 200 meters. The expected transmission loss in decibels over a flat Earth is given by the following equation. We get down to page 14 here. HH propagation through the woods. In taking the HH polarization propagation data through woods both in winter and summer, we observed local fluctuations up to 20 decibels. We avoided these large dips in receive power by minor repositioning of the receive antenna. It is important to note, however, that the multipath from the local trees and brush can cause such variations. After the data were inspected, it became apparent that they tended to agree with the theory given by equation 2 plus some fixed attenuation, and therefore allowed us to develop an analytical expression based on flat earth theory. I'll read that again. Therefore allowed us to develop an analytical expression based on flat earth theory. So everybody who wants to label us flat earthers crazy must have to lump in the Army Research Laboratory as part of the Looney Tune bin. Let's see what else they have to say. Propagation of electromagnetic fields over the flat earth. What? Army Research Laboratory, arl.army.mil, by Joseph R. Melita, February 2001. Propagation of electromagnetic fields over flat earth. You guys seeing that? Check it out. There it is again. In the table of contents, figures 6 and 7, comparison of principal fields from an ideal dipole oriented perpendicular and horizontal to a homogeneous flat earth. Figure 7, comparison of principal fields from an ideal dipole oriented perpendicular and horizontal to a homogeneous flat earth. There are the two figures, figure 6, figure 7, over flat earth. Army Research Laboratory. Back to NASA. NASA.gov. June 2002. Stability and control estimation flight test results for the SR-71 aircraft with externally mounted experiments. So we're back to checking out some things on the SR-71. And we get to page 9. Methods of analysis, parameter identification formula. Go through some formulas right here. And it says equations of motion. We come back to that once again. These equations assume a rigid vehicle and a flat, non-rotating Earth. For the SR-71 with external hardware attached. Back to the Army Research Laboratory, August 2002. Automatic target acquisition of the Demo 3 program. Demo 3 program, Army Research Laboratory. The detection algorithm. The algorithm described in this report was designed to address a need for a detection algorithm with wide applicability, which would serve as a pre-screener/detector for a number of applications. While most automatic target detection/recognition algorithms use much problem-specific knowledge to improve performance, the result is an algorithm that is tailored to specific target types and poses. The approximate range to target is often required, with varying amounts of tolerance. For example, in some scenarios, it is assumed that the range is known to within a meter from a laser range finder or a digital map. In other scenarios, only the range to the center of the field of view and the depression angle is known, so that a flat Earth approximation provides the best estimate. Alrighty then. January 2003, back to the Army Research Laboratory. See, up arl.army.mil. January 2003. Scrolling down to the report document page, talking about the scanning fast field program and I guess the various models. The geometry profile is required because of the angular dependence of the sound speed on the wind direction relative to the direction of propagation. This model works over a flat Earth and non-turbulent atmosphere. Wonder how it works in a turbulent atmosphere over a spinning ball. Okay, September 2009, Army Research Laboratory. Computationally efficient algorithms for estimating the angle of arrival of helicopters using acoustic arrays. And on page 22, The estimated phases of the reflection coefficients have a dependency on range. This may be caused by a violation of the assumption of the flat Earth model. So you're having some discrepancies when you violate the assumption of a flat Earth model? And let's see, one last one. From the Army Research Laboratory, March 2010. Projectile Field Dynamics, page 1. The 6-DOF rigid projectile model is employed to predict the dynamics of a projectile in flight. These equations assume a flat Earth. Why would you project flight dynamics over an assumed flat Earth if in reality we are dealing with a spinning ball? It seems to me that the Army Research Laboratory and NASA and the Russians and the CIA have been talking about flat Earth long before any of us showed up. Kind of makes you wonder, what do they know? Thanks so much for watching. I hope you enjoyed this video presentation. If you did, please subscribe to my YouTube channel, like the video, and share it on your favorite social media sites. There's a lot more to come, so stay tuned and we'll see you back next time.